the x squared minus 1 over the 2x minus 3. Now let me go ahead and figure out what this was. This was 2x plus 2h minus 3, and this was 2x plus 2h minus 3. And then all of that over h. So what we need now is to multiply that out, and that's just an algebraic exercise, which you would do just so to remind you, you'd go here times this times this times this, and then you would go this times this times this times this, collect all your like terms together, then this times this times this, then this times this times this, and you put all that together. So to spare us the work of seeing all that multiplied out, I'm just going to write out what that would become. We should have a 2x cubed plus 4x squared h plus 2xh squared minus 2x minus 3x squared minus 6xh minus 3h squared plus 3, and then minus, here's where that minus came in, so I'm at this point right here. Minus, I'm going to probably run out of room here. In parentheses, I'm going to put it all in parentheses because I have to subtract it all. So I'm actually doing this part of this right now when I multiply all that out. That would give me 2x cubed plus 2x squared h minus 3x squared minus 2x. I'm getting smaller here as I'm running out of room. Minus 2h, and then plus 3. All right. All of that over the common denominator, which would be, this is the common denominator in both, so I'm just going to write that below this. 2x minus 3 times 2 times x plus h minus 3, then all of that divided by h. My goodness. This is what makes calculus so challenging, is all this algebra. All right, so when we start to put this all together, things start to cancel. This 2x cubed, this 2x cubed. Let's see, what else cancels here? We've got a negative 3x squared, negative 3x squared. We've got a negative 2x, and then this one, negative and negative becomes positive. The 3's at the ends cancel. And what else? I believe that's everything that cancels. What we should be left with is limit h goes to 0 of, let's see, 2x squared h plus 2xh squared minus 6xh minus 3h squared plus 2h all over our common denominator. Our common denominator was 2x plus 2h minus 3 times 2x minus 3. That's just all I did here was distributed that through. So that's why it looks like this right here. And I switched the order of them, no big deal. All of this divided by h. What you'll notice now is that every term in the numerator has an h in it, so you can factor an h out, and then they cancel out with the one on the bottom. So you'll get limit h approaches 0 of, oh my goodness, I apologize, I've got the Spurs game on in the background. I'm getting distracted. So when we cancel an h, we get 2x squared plus 2xh minus 6x minus 3h plus 2 all over our common denominator, 2x plus 2h minus 3, and then 2x minus 3 here. So the h went away on the bottom. And now finally we can let h go to 0. So when we let h go to 0, certain terms will vanish. This term's gone, this term's gone, this term is gone. And so what we're left with is 2x squared minus 6x plus 2 over 2x minus 3. That's 2x minus 3, and then another 2x minus 3, so squared. Ooh, okay, there we go. All that work. This is the new function that you get when you take the derivative of that original function. A lot of work there, lots and lots of works. That's the extent of 2.2. We're going to move into 2.3 next, but I'm going to take another quick break. Sorry. Okay, the homework for 2.2 is going to be a lot of algebra, a lot of what you've seen me demonstrate, like in the previous problem. But you know, it's kind of like the torture session of Cal 1. 2.3 is where we finally get to a place where we can get some shortcuts and not have to do that big long limit that we've been working with. This section is about the differentiation formulas. We love formulas. All right, so let's go through these. All right, there's going to be a couple of them. So the first formula for taking derivatives is this one. And I'm going to use a different notation. It says if you're going to take the derivative, so this is using an alternate notation here. Oh, I'm getting a call. Gosh, I apologize. All right, so this notation means I'm going to try and take the derivative, okay, the derivative with respect to x, meaning that x is my variable. And here's what I would like to take the derivative of, a constant, c. Well, let's think about that for a second. If you have a function that's constant, that means it's just flat line, it's always some value c, then the slope of the tangent line at any point, right, pick any point, the slope is always 0. It's flat. So the derivative of a constant is always 0. Okay, so that's a formula. It makes sense. Visually, it makes sense. But how can we show that with the limit? Okay, so let me show you. Let's start with a function that is constant. All right, and now let's try and find its derivative. The derivative would be the limit as h approaches 0 of f of x plus h minus f of x all over h. But the limit as h goes to 0, what is the function's value at x plus h? Well, it doesn't matter because that function spits out c all the time, minus the function's value at x, but that doesn't matter because it always spits out c, all divided by h. And now what we get is c minus c is 0. Now, we're not saying it's approaching 0, we're saying it is 0. And therefore, the limit as h approaches 0 of 0 over some very small number, this will be 0. Very important that you understand that before, when we were saying 0 over 0, we were saying the top was approaching 0 and the bottom was approaching 0. Here we're saying the top is 0, and 0 divided by any number other than 0 is 0. So we get 0. So that matches with what we got visually. Okay, next formula. 2. What is the derivative, treating x as our variable, of the function x itself? Well, again, let's take a look at a graph. The function x is the identity. It's the perfect diagonal line. And if we go to any point on this line and we look at the slope is always 1, right? Rise over run, up 1 over 1. So the answer to this should be 1, which it is. Now, how can we show that? Again, the derivative will be the limit as h goes to 0 of f of x plus h minus f of x all over h. Now keep in mind the function we're actually using here is the function f of x equals x. So whatever you plug in is what exactly comes out. So this top left corner, when I say what do I get when I plug x plus h in? Well, it should spit out x plus h. So this is limit h goes to 0, of x plus h, and then minus, what do I get when I plug in x? Well, it spits out x, and then all over h. The x's cancel, and you get h divided by h. H divided by h is 1. So limit as h goes to 0 of 1 equals 1. And that's because in this expression 1, h doesn't appear. Therefore, h doesn't make anything vanish. So you just get 1. And again, that matches up with what we got earlier. So I'm trying to show you this is the formula. The derivative of x is 1. But we can show why it's true by using the limit, proving it. All right, the next formula is a very powerful formula. It's called the power rule. It says, what is the derivative with respect to x of not just x, but x raised to some power, n? And the answer is n times x raised to the n minus 1. So what I want you to see happens here is that when you have x to a power and you want to take its derivative, the power comes out front. The x remains as the base, and then the exponent is now that power you had before, but take 1 away from it. Now, I'm going to think about whether or not I want to show you why this is true. Let me first show you some examples of this, and then I'll decide if I want to show you why it's true. So here's an example of this. Let's say you have f of x is x squared, and you're asked to find f prime of x, the derivative. Well, since we have x being raised to some power n, we can apply this formula. So the derivative